Let's begin the second part of the operators in quantum mechanics. Let's see some properties of operators. As you have seen, in case of addition, both commutative and associative law is followed by operators. The first one, the A plus B is equal to B plus A. This is the commutative law. And the second one, A plus B within parenthesis plus C cap equal to A cap plus B cap plus C cap within parenthesis. So this is the associative law. Similarly, in multiplication also, it follows the associative law. Okay, as you have seen here. Very important thing which we have to learn in case of operators, the commutation relation. I have taken here two operators A cap and B cap, and for A cap and B cap we can write the commutation relation as within the square bracket A comma B, okay, A cap comma B cap equal to A cap B cap minus B cap A cap. So this is the commutation relation. Okay, so if you write the same relation for B cap and A cap, it will be what? It will be gives you in this way: B cap A cap minus A cap B cap. So comparing these two equations, you can easily write this equation. Okay, so they are negatively related. Okay, now if operator A and B are multiplicable and both of these follow this relation, that is, this relation is satisfied by the operators A cap and B cap, so in that case we can write this. Okay, it is A and B are commute to each other. Okay, let us see another important thing related to operator. So as you have seen, I have written here a function psi x is equal to small a function psi x. Okay, so here A is your operator and psi x is called the Eigen function and small a is the Eigen value. Okay, so how we can write this equation? Actually, normally what happens when you operate any function, suppose psi x, by any operator, suppose A, you will get this type of relation. Okay, and here the constant A is not an arbitrary one, it is a peculiar one. That is, peculiar means it is associated with this Eigen function. Okay, you cannot take it arbitrarily, and so it is named as what? Eigen value. That means whenever the operator A operates on different kinds of functions, okay, your Eigen value will be different. Therefore, you can write it in general term as A psi m x to A m psi m x. Here the values of m ranging from 1 to 3 like this. Okay, so from this equation what we have understood that for every value of m there is a different Eigen function and different Eigen value. Okay, in some cases this kind of equation also found, that is, for different Eigen functions we have only one Eigen value. Okay, as you have seen, I have not given any suffixes here. So for different kinds of eigenvalues, you get one eigenvalue. So in that case, the equation is called a degenerate equation. Okay. So degenerate means you have this kind of function psi 1, your eigenvalue will be a. For psi 2, your eigenvalue will be a. So similarly, for all the eigenvalues, you get the same. For the all eigenfunctions, you get the same eigenvalue. So in that case, what we call this equation? This equation is a degenerate equation, and the states that means these states, these are called states psi 1x, psi 2x, these are also called states. Okay, so they are degenerate states. For example, you can consider hydrogen atom. Okay, for hydrogen atom, you will get specific energies for different states. I mean, the first level, second level, third level, you get different kind of energy. As you know, for the first level, it is 13.6 eV. So like this. Okay, and for the second one, you can calculate it for the second one. Okay, and from the second one, you will get the vibrational states. Okay, vibrational states, rotational states. It will be clear when you read atomic physics. Okay, so for every vibrational states, your energy will be same. Okay, that means here energy E is your eigenvalue. Okay, an interesting linear operator, the Hermitian operator. Okay, so suppose I have taken an operator A. Okay, and two functions psi mx and sin x. Now if the operator A follows this relation, it is as I have written as integration with the limit is minus infinity to plus infinity, psi m star. You know what is psi m star? This is the complex conjugate of this function. Okay, a psi n dx equal to, within bracket, a psi m star sin star dx. So if you expand this, you will get a star. A star here also. That is, a star will be your what? Will be your complex conjugate of the operator A. But since it is a Hermitian operator, you will find it what? You will find it A star equal to A. And since this is happen in case of this operator, so it is Hermitian. So for your easy memorization, you can take this or you can follow this. That is the complex conjugate of A equal to the A. So if this relation is follows, then your operator will be what? A Hermitian operator. This can be written in bracketed form also. That is, I have taken here this parenthesis psi m comma a psi n equal a psi m psi n and equal what? Psi n a psi m star. So there is two important theorem related to Hermitian operator. So I have shown here the theorem. Theorem 1, the eigenvalues of Hermitian operators are real. And the second one is any two eigenfunctions of a Hermitian operator that belongs to different eigenvalues are orthogonal. Okay, I think you understand these theorems. Okay, so now we will prove these two theorems one by one. Now to prove the first theorem, let us consider a Hermitian operator A and its eigenvalue equation. I have written just A psi n equal to, where your small a n is what? Is your eigenvalue. Okay, and this is your eigenfunction psi n. Okay, now taking the inner product of this equation with psi n. Okay, so how we can take inner product, or in how we can show it? This psi n a psi n equal a sin sin. Okay, so this is equal to what? This is equal to an, isn't it? How we can find an? Are you getting? Okay, this is this term equal to 1. Okay, how this term equal to 1? As you know, this can be written as sin star sin. Okay, and this is suppose I have taken here x, variable is x, and this is equal to what? This is equal to 1. Okay, now since your operator is an Hermitian operator, is a Hermitian operator, so we can write it sin a sin equal to a sin equal to sin, but this will give what? This will give you a star sin. I think you understand how we will get a star. Okay, so again this will gives your a star term. I just forget writing n, suffix n. Okay, that means eigenvalues of Hermitian operators are real. Now what is your second theorem? Any two eigenfunctions of a Hermitian operator that belong to different eigenvalues are orthogonal. Now let us prove this theorem also. So to prove this theorem, suppose we have two eigenfunctions psi m and psi n, and I have taken an Hermitian operator, suppose A. Okay, and corresponding to these eigenfunctions, your eigenvalues will be suppose am and an. Okay, so for these two eigenvalues we can write the eigenvalue equation in this way: a psi m am psi m into a psi n equal to an psi n. So this is the eigenvalue equations. Now take the inner product of this equation with function psi n. So when you take the inner product, you will get this equation. Okay. Now, since operator A is a Hermitian operator, so these equations, that is, we can write this one in this way also. Okay, as you have learned. Okay, so this will result you A psi m equal to A n psi m. So from these two equations, how you can write A n psi m equal to A m psi m. Okay, we get what? A n minus A m psi m is equal to 0. Okay, as we have known, A n not equal to A m. Okay, why? Because they are two different eigenvalues associated with two different eigen function. So to satisfy this equation, psi m, this product must be equal to 0. Now what is this? This shows that the eigen functions psi n and psi m are orthogonal to each other.